This is Project 5, video number 1, pencil and paper part. Let's see, supposed to write a function. First thing we got to do is write a function to calculate the electric potential due to a couple of point charges. 50 nanocoulombs at 0, 0, plus 0.005 meters. And so two charged particles, looks like a centimeter apart. Alright. Let's try that. So here's our situation. I think I'll call this the X, Y, and Z directions. We got a charged particle here, charged particle here, a distance A equals 0.005 meters. Well, I think I'll try to squeeze arrow inside there. Equals 0.005 meters. This is charge minus Q. Charge Q, where Q is equal to, I think it was 50 nanocoulombs, so 5 times 10 to the minus 8th coulombs. If I multiply by 10, I get a 50 there. Got to compensate by dividing by 10, 10 to the minus 9th, and that's 50 times 10 to the minus 9th, or 50 nanocoulombs. Yep, that's what they said. Alright, so we want to find phi at this location. Distance R, call it R plus, from the positive charge, and R minus. So phi is going to be equal to phi to the positive charge plus phi to the negative charge. I want to call those phi 1 and phi 2 when you write it up. KQ over R plus. I'm going to say minus KQ over R minus. So Q itself is 5 times 10 to the 8th, 5 times 10 to the minus 8th coulomb. So I got that here and a minus that in the second term. Okay. R plus, to get to the point P where I'm calculating what phi is, there's point P at X, Y, Z. I gotta go, I don't have to go up as high as Z, I gotta go up Z minus A, and other than that, it's like I gotta go all the way over X and all the way back Y. So let's put it up here. R plus is equal to square root of X squared plus Y squared plus Z minus A squared, where that A is the 0.005 meters, and R minus, I have to go an extra distance A. This A is a positive value, it's not the ordinate. No, it's not the actual Z value, it's just how far down you gotta go. So in other words, the this point is at 0, 0, minus A. So at any rate, to get up to point P, I have to travel an extra distance A along the Z-axis. So this will be z plus a squared. And so a is a given. I think I'm ready to say init my outline for phi, which is what I'll name this function. Init a the x, y, and z are arguments. I'm going to go, well, that's what it is. X, comma, y, comma, z are arguments. I think I'll make this the vector a, so I think I'll make that 0, 0, 0.005. That's what I'm going to call a. It's an array a. Is this array of values is an argument? So the user gives us those values, and then I'm going to go 3. At least I'm going to try this. I'm going to play with this in MATLAB, but yeah, R, call it R plus, so I'll call it RP here. For R plus is the norm of I want the norm of our argument, and our argument is an array. And I think I got to play around with that a little bit in MATLAB. So even to see where I'm going to go here in this preliminary part, I want to look in MATLAB. So I'm going to write a little test function. I'll call it getMag. So function mag r mag r equals mag of r. And let's see, I think mag r equals norm of r. And let's try saving that. I'm going to go ahead and save that. And it's saved. And now I'm going to try to run it. Got to get to the right directory. And I'm going to create a vector rvec equals 1, 2, 3, and go mag of rvec. and it says mag of rvec is that, and I'm going to check to see if that is the magnitude of that vector on the calculator, see what the square root of 1 squared plus 2 squared plus 3 squared is. And yeah, I get that same exact number. So in here, like, there's nothing that says that R is a vector. I just have to know that it's a vector, or an array containing 3 elements. So that's what I wanted to check on. Alright, so let's get back to here. I'm going to say R equals a 3-dimensional array. Not sure you can read that equal sign. Equals the 3-dimensional array x comma y comma z, and it is the argument. That word right there is hard to read. Is the argument of phi. So then RP is, I want the norm of R minus A. So when I subtract this array from that array, I get an array that has the elements x minus 0, which is x, y minus 0, which is y, and z minus 0.5, which is exactly what I wanted. Okay. And then R minus, that's a little further away. RM, we'll call it. So the distance that we are from the negative charge, this one down here, is going to be the norm of R plus A. So phi is phi of R, where R is an array of 3 elements. Okay, and then init k, initialize k equals 8.99 times 10 to the plus 9, and q is equal to, I go 50 times 10 to the minus 9 coulombs, and this is Newton meter squared per coulomb squared. And then 5 here is phi I want to call my function phi, so I'm going to call this phi val. That's going to be my return variable name, is equal to, so k, this is k times q times 1 over r plus minus 1 over r minus. K times q times 1 over r p minus 1 over r m. Alright, that's the easy one. Alright, now I gotta find E. Find E at a position given by the vector r, which will be an array x comma y comma z. J comma z times k. Well, these should be pluses. So here's our idea. It'll be x, y, z. Here's the point P where I want to find it. It's up here at a distance r from the origin. And the way I'm going to go is I'll find phi here and here and subtract the two. So I'll get e sub x is minus delta phi divided by delta x, which is minus phi at x minus a little bit. What am I going to call my call it HS. Let S, I think I'll call it S, be the step size. So this will be S over 2. And then comma y, comma z, and then minus phi at x plus s over 2, comma y, comma z. And that's going to be all divided by delta x, which is my step size, which is s. Alright. Similarly for the other two. So I think I might as well write that down. EY is minus delta phi by delta y. So I want to step in the y direction from a little bit before the value of y to a little bit after. So it'll be minus, and then minus this fraction, phi of x comma y minus s over 2, half a step, comma z, and then minus, I think I went the wrong way. As I step in the positive x direction, I'm going from here to here, so I take my final position minus my initial position. So this is a minus sign right there. So I go plus this, and then minus the phi at the initial position to get the change in phi, x, y minus step size over 2, and at z, all divided by the step size, and ez, which is minus delta phi over delta z, is going to be, and the delta phi, how much it changes, because only z changes is the idea, so we only let z change. Phi of x comma y comma z plus step over 2, half a step, minus phi at minus s over 2. And then that's all over the step size. And so E vec is equal to EX comma EY comma EZ. And I think I'm writing it as if I were writing the code outline. I think I'll write E equals EX I plus EYJ plus EZK. So what do I gotta do? I gotta initialize S. Phi is I think to actually to do this, I know I'll include it in the code outline. So code outline. Line for function E of R, and I'll just go at E of R, where R is a 3-element array. So I'm going to create 3 little vectors, 3 change vectors. Let's see. 1 init S equals 1 millimeter, so 0.001 meters. I think that was, we were told what S had to be. Calculating, use a step size of 1 millimeter, right here. So 1 millimeter is 0.001 meters. Define dx is an array, which is 0.001 comma 0 comma 0. So this is like a vector. dy is equal to 0 comma 0.001 comma 0, and dz zero comma 0.001. Hope some of you do it on your own, because there are so many very different ways of doing this that are all correct. Like this using the norm, you could go r of 1 squared plus r of 2 squared plus r of 3 squared square root, where r of 1 means the first element of the array, r of 2 means the second element of the array. But here's the way I'm doing it. So then let's see if I got this. EX equals phi of R plus dx minus phi of R minus dx, all divided by S. Okay, remember phi is built to take an array. So this is the array x comma y comma z, where x comma y comma z are the coordinates of the position where they want us to calculate E. And I add dx. So the dx is 0.001 comma 0, comma 0. No, this should be 0.1 over 2. So I'm going to call that s over 2. S divided by 2. This is s divided by 2. This is s divided by 2. I wanted half a step size for each of these. So I go half a step size ahead and half a step size behind, and now I've got just the idea that I had up here. You know, half a step size for bumping up x, and then half a step size down here. Alrighty. I guess I don't really like the name of it. dx is the same as s, so call it h dx, half of dx, half of dy, half of dz. H, and then ey is phi of r plus h dy, half of dy, minus phi of r minus h dy, all over the full step size, the dy itself, which is what s really is. Alright. And then ez phi r plus h dz minus phi of r minus h dz, all divided by dz, which is s. Then what I want to do is to return e vec. So I think I'll call it is ex comma ey comma ez. Alright, I think that's all that there is. So we got two functions, got the code outline for each one. I got what I consider full algebraic solution here. I'll write in return this is what I'm returning to the user. Phi val kq over r positive minus kq over r minus is what it's equivalent to. So I think that does it for the pencil and paper part. Obviously, if I find mistakes as I do the coding, then I'll come back and correct those, but I think it looks good for now. That ends Project 5 video number 1.